So today we're going to take a look at volume. And the basic idea of what we're going to do today is called the disk method. We're going to see another method, a variation of this called the washer method today. But here's the basic idea. We're going to take what we know about area. And we know about area is all these integrals, right? Being able to find these integrations. And we're going to imagine that we take this two-dimensional shape and we spin it. So you're just going to, it's sort of like spinning a top. You're going to spin this object, okay? When you spin this object, it's going to be called a solid of revolution. The line that you spin it around is going to be called the axis of revolution. And the simplest object that exists of this type is called a disk. And to help you visualize, you can say thank you that I'm not going to draw it for you. Because I don't draw well either. But we're going to watch a video where they do a very nice job of drawing the picture so that hopefully you will be able to visualize it without me drawing anything. Okay? All right. All right, so after viewing that video, you have this sort of image in your mind of what happens when you rotate these objects. And he showed you how to rotate it both around the x-axis and the y-axis. And we're going to take a step further and rotate it around some other lines as well. But the x-axis and the y-axis is a good place to start. So let's go back to what we were talking about, or what he mentioned in the video. First, as a reminder, how do you find the volume of a cylinder? What was that basic formula? Right, pi r squared h. And that is exactly where our formula comes from. So h is the height of the disk, and our disk is getting smaller and smaller so that we get more and more disks inside of our region. You saw his picture where he increased his disks. And so as that happens, we end up with a volume that still has the pi, but our height gets replaced by either a dx or a dy, and the integral between wherever it is that we're starting and stopping on the particular graph that we're working with, a to b. And the part that's inside is r squared, and r squared is simply the radius of whatever cylinder it is that we're looking at. So if we're dealing with and rotating around an x-axis or a horizontal line, this is r of x squared. And if we have a vertical line or the y-axis, go from a to b, and we're going to be using our radius with respect to y. And it looks like that. All right, so it will help us to actually take some functions and take a look. And this is one where we actually saw him use this particular function. And so we're going to start with this particular function and take a look. So when you're drawing, or when you're working with these, what do I expect to see? Well, I don't expect to see three-dimensional drawings, okay? But what I do expect to see is the representation of the area that you're referring to. And it will help you a whole lot if you draw the axis of rotation curved, sort of like an arrow in there, like what he did too. So the first thing we're going to do is we're going to think about what this looks like in 2 dimensions, so the two-dimensional area that this is referring to. And this particular one is a very familiar to you graph, or at least it should be. And it's half of a parabola, looks something like that, right? Okay. We're going to go from 0 to 3 on the, and I'm sorry, it says that function, and I don't have it drawn in here, but the line y equals 0 is where? The x-axis, right, yeah, not y, it's actually the x-axis. So we're going to be bounding our function between the curved x squared function and the horizontal axis, okay? And then it says that we're going to go out to x equal to 3, and if I come over here to x equal to 3, like so, then I can see that the line x equal to 3 is actually this one, and you've got a bounded region now, right? So it's this piece right here. This is my region that I'm going to be integrating, and I'm going to be rotating. Now, it says that we're going to rotate this around the x-axis. So the x-axis is my horizontal axis, and it looks something like this. Now, he mentioned in his, in fact, let me change this for a sec. We'll try that. He mentioned in his video presentation 2 or 3 times that we need to draw a representative rectangle. And the rectangle is always drawn how?
perpendicular.
Perpendicular. Yeah. Perpendicular to what, Taylor?
The one we're rotating.
The one we're rotating around. So when we're using the disk method, and in a moment when we're using the washer method, we're always drawing representative rectangles perpendicular to where we're rotating around. So since I'm rotating this around the x-axis, we're going to draw a representative rectangle that's going to be a vertical rectangle. Let me try this. Oh, that was too big. There we go. I'm happy enough with that. There's my representative rectangle. All right, so we're going to identify some of the features in here just like he did. Since I'm rotating this around the x-axis, the width or height, as he kept referring to it, of my rectangle is actually delta x, which means I'm going to be integrating with respect to dx, right? My integral sign goes from pi, has a pi in front of it, and then I'm going to use limits of integration that reflect the x values. So what is the smallest x value represented by this region? 0. And the largest one? 3. Perfect. And then what's going on inside is actually however long or tall, this sort of looks like right here, my rectangle is. So this yellow rectangle is actually going to be a distance of y, isn't it? I mean, that's how tall it is. It's y units away from that axis. Well, this is supposed to be y, and y is the square root of x. Right? It's the square root of x because that's my function that I started with up here. So my radius, if you will, is actually square root of x. And then I'm supposed to square my radius in order to use this area formula from cylinders, or volume formula from cylinders that you have used way back to probably somewhere in middle school. All right, so let's get it going. What in the world is the integral, or what is the simplification of the inside of this integral first? Yeah, this is just x from 0 to 3. So what's the integral? All right, pi and then x squared over 2, and we're evaluating from 3 to 0, or 0 to 3. So the pi stays on the outside. I'm going to plug my 3 in, so this is going to be 3 squared over 2 minus 0 squared over 2, which is highly uninteresting, but that's okay. And what is 3 squared over 2 going to be? 9 halves, and then times the pi. So this is 9 pi over 2. Any questions on that one? Okay, we're going to keep using the same function throughout this entire lesson because the issue is not so much the integration of what we're doing, it's the setup of what we're doing. Okay? So let me extend this idea first so that we can go to the next piece. So I mentioned that we are going to extend this idea to include washers. I don't know if I... All right, so when we take a look at the volume that he had talked about in this, it was actually pi, and we would have the outer radius squared minus the inner radius squared times the width or the height of these different rectangles. So your book uses W, so I'm going to use W for width. And then when we do that and we extend that idea as W goes to 0, as the widths of these things get infinitely small, we do get an integration, and we would have pi times the integral from a to b. And we have the outer radius, which they call capital R of x squared, minus the inner radius, and they're going to refer to that as lowercase r of x quantity squared. And we subtract those two from each other, dx. And I'm not going to write down the one for dy because you just change all the x's to y's. It's the same thing, right? So we have to determine, again, using perpendicular rectangles, which one we're using. Are we integrating with respect to x or with respect to y? So let's take a look at the same function we had before, same picture. We've got our function of x squared, and we're going to be integrating that around a different axis now. So my same picture looked like this, went from 0 to 3, and the picture was in here. So far, so good? The difference is that this time we're going to integrate this and we're going to rotate it around the y-axis. So when I rotate this around the y-axis, my picture is actually a little different than the example he did. His example actually started at the y-axis, one of them anyway, from the last section, and it went out to the function. But I have empty space there, right? We're actually imagining taking the 3, where the 3 is the blue part, and we're spinning that instead. So I'm sort of getting something that's hollow, right? It's got a hollow, kind of a cone-like shape in the middle of it a little bit. And so our representative rectangle, how will it be drawn, horizontal or vertical? It's horizontal this time. So here's my representative rectangle, something like that. And as I look at that representative rectangle, that tells me that I'm integrating with respect to what on this one? Y. Which means eventually I need to get this equation to reflect x equals. So what will x equal? It'll be y squared. Okay, so I'm going to need that in a moment. Now that's not exactly what I need, but I need part of that. So let's take a look again. So I'm supposed to have this function's volume that has a pi in it. I'm integrating along the y-axis, so this is 0, and I'm supposed to go up to wherever this peak is right here. So what is this number right here? The top corner of my graph. It's square root of 3. My x value is 3, right? But my function is defined as y equals the square root of x. So I'm actually going to be going from 0 to square root of 3. Okay, so far so good. And my outer radius is actually this whole piece right here. That entire piece. Which actually, it isn't what we had just said. It's not y squared. What is the distance from there all the way out to the edge of my blue graph? It's actually 3, isn't it? So my outer radius is actually 3, which we are then going to square. My inner radius is this piece right here. Just that little blue piece right there, which is a distance of x. Agreed? And what is my x value? Y squared. So there's where the y squared is coming into play on this one. So this is 3 squared minus y squared squared that we are going to integrate with respect to y. Okay, let's clean this up. So we have pi on the outside. I'm integrating with respect to y from 0 to square root 3. On the inside, what do I have? 9 minus y to the 4th. We can integrate that without too much difficulty. So what is the integral of 9? It'll be 9y, good. And the integral of y to the 4th? Good, y to the 5th over 5. And we're going to evaluate that at square root of 3 and at 0. So we're going to have to work a little bit with radicals on this particular one because they don't just all disappear. All right, so I'm going to plug in the square root of 3 into this. And then plugging in 0, of course, is very nice on most of these because we're dealing with polynomial functions primarily. So if I plug in the square root of 3, I have 9 square roots of 3 minus square root of 3 to the 5th over 5. And all of that is actually minus 0. Because when I plug 0 in, I get nothing, right? Is that good so far? Okay. All right, so I need to simplify the square root of 3 to the 5th. Does anybody know? It is 9 square root of 3, and it's still over 5, right? Yeah. Okay, so basically the square root of 3 squared would have been 3, and I've got 5 of them, so I have square root of 3. This one's 3 and this one's 3. So there's the 3 times the 3. It's showing up on the top of the screen if you're following. Those are each 3. And then I've got the square root of 3 at the end. So I've got 9 square roots of 3 still over the 5. If I get a common denominator, it would be a denominator of 5. So this piece down here would become a 5. And the 9 would become a 45. So what's 45 minus 9? 36. So I have 36 square root of 3 over 5 pi. Any questions on that one? It's not the integration that will cause you problems, right? It'll either be the setup or the simplification, depending on what we're working with. This one, we had some potential for some problems because we had that radical 3 in it, but the setup is the most important part.
So the reason we did radical 3 was because of the y equals square root of x? Is that why?
Yes, why we did radical 3, like right here, you mean?
No, on the like graph. On the,
Yeah, where we put it up there. It's because we're integrating with respect to y, which means my limits of integration have to correspond to the y values. So the x values went from 0 to 3, which corresponded to y values that went from 0 to square root of 3. Yep. Okay, let's take a look at another one. Same function. I'm going to be dealing with the same function this entire section, okay? So I've got that same square root of x function. Same piece of it's shaded in. I go all the way over to 3. But now I'm going to integrate around what line? The x equal 3 line, the vertical line that I just drew in, right? Okay, so that's a little different. So let me draw that in a different color so we remind ourselves. We're actually going to be integrating around this line, like so. So let me first ask you, is it a disk or is it a washer? It will be a disk, okay? Will my representative rectangle be horizontal or vertical? Horizontal. Why?
Because it's to where you're rotating it around, perpendicular.
Yep, got to be perpendicular. So the rectangle that we draw will always be perpendicular. Yes?
How did you know it would be a disc?
We're going to get there.
Okay.
Yeah. So if I take this right now and I rotate it around, the reason I know it's a disk is because as this rotates, I don't get anything hollow inside. A washer has a hollow inside. And this one, when I rotate it, imagine, I'm going to try drawing a picture and then I'm going to immediately erase it because it's going to look terrible, okay? So imagine that if I drew the other side of this and I somehow rotated the object, it would sort of have this bowl shape to it, right? It would look like an upside down bowl that's filled in. So imagine filling the bowl in with some sort of a sand or a cement or something like that. That's the image you've got. You don't have a hollow shape inside. You've actually got a filled in shape. So we've got a disc. Okay. Well, it could have been a worse picture, I think.
That was pretty good.
Yeah.
It wasn't too bad. All right, but I need the space, so I needed to erase it. All right, so let's take a look. I've got that disk formula now, so I don't have to do an outer radius minus an inner radius. However, the radius that I have is slightly different than you might be expecting. So we've got our volume. It's supposed to be pi from 0 to something. Well, let me pause for that in a moment. Is this going to be with respect to x or y?
Why?
It will be with respect to y. And we already found a moment ago that that means we're going to go from 0 to pi over 3, or to 0 to square root of 3. Because this is going to be from y equals square root of x, it's going to become x equals y squared, right? Okay, so I'm supposed to find out what my radius is. Well, the radius in my picture is this piece right here. I'll just call it r for now, for space. So here's my radius. How do I find out what that length is? Can you tell? Yeah. Okay, so let me draw it up a little bit further so I have some more space to write in. This whole distance right here is 3, right? This distance right here is square root of x, right? So the distance that I'm actually wanting, this piece right here, is going to be 3 minus the square root of x. Okay, so can you picture it? We're going from here to here, it's 3. This piece right here is square root of x. So the piece that I want, the missing piece, is 3 minus the square root of x. But I don't want it to be the square root of x because I've got it represented in terms of y, so mine won't actually say 3 minus the square root of x. What will it say? 3 minus y squared. All right, so my radius here is actually 3 minus y squared squared. dy. Okay, is everybody okay with that? It looks a little funny the first time you see it, and we're going to do another one, I think, here in a minute, too, so hopefully it'll help to cement that idea. All right, so on the right-hand side, though, the fact that this is squared means you've got some algebra to do before you integrate. Don't go trying to integrate this. You don't have any properties that allow you to do that. You need to actually square that out on the right-hand side. So you'll remember things about like FOIL or distribution. And if you do that properly, you should be getting 9 minus 6y squared minus y to the fourth dy.
Shouldn't be plus one.
Oh, yes, it is. I'm sorry. Thank you. Plus y to the fourth. Perfect. Okay, then we can integrate without any difficulty. All right, so let's integrate this. 9 becomes 9y. 6y squared becomes what? It becomes 2y cubed, actually, right? So the y squared becomes y cubed over 3, and the 6 and the 3 simplify to 2. How about the y to the fourth? Y to the fifth over 5. Good. And our limits of integration are square root 3. Man, I sure wish we could get rid of that square root of 3. And 0. So we're going to have to deal with some square root of 3's on this one as well, but I like dealing with 0. It's one of my favorite friends. How about you? Yeah, for sure. Pretty nice guy. Okay, so we're going to evaluate 9 square root of 3 minus 2 square root of 3 cubed plus square root of 3 to the fifth, which we've already done, over 5. And all of that's actually minus 0. We'll put it in just for the sake of reminding ourselves that we did check that. It actually is 0 when we plug 0 in. All right, so I have 9 square roots of 3. What does 2 square root of 3 cubed become? So this is minus 6 square root of 3. And then I have square root of 3 to the fifth over 5, which we did a moment ago was 9 square root of 3 over 5. And are you guys okay with me simply telling you what this is? If we were to get a common denominator and so forth, this would become 24 square root of 3 over 5 pi. Okay? You guys are going to hate this function by the time we're done. All right, we're going to do it again. But we're going to do a different line or axis of revolution. All right, so here's my function, over to 3. It's shaded in. Not about you, but I like that blue. It's a very pretty color, isn't it? And then I'm supposed to now rotate around the line x equals 6. Where's that? 3 over that way, isn't it? So over here, somewhere like this, I've got this line 6, and it looks like this, and I'm supposed to be rotating this shape around this line. It is going to be hollow, isn't it? Yep, going to be hollow this time. My representative rectangle, horizontal or vertical? Horizontal. Man, I should get away from those, shouldn't I? Because that means I have to deal with that square root of 3 again, doesn't it? Okay, is this a disc or a washer? This one's a washer because you guys told me just a minute ago it's hollow, right? So this one's integration, still going to go from 0 to square root of 3. And I need the outer radius. Well, what in the world is my outer radius going to be on this one? Is it 6? Okay, say that louder for me, Jordan. Okay, so where are you getting 6 minus square root of x? Can you tell me?
The distance from the line of 6 to the function of the square root of x.
Okay, so here's 6. Oh, that's not a good picture. I want it down further. Let me just use the blue. This one's 6. I'm supposed to be finding this piece right here, right? It's not drawing it. We'll give it a sec. I don't need the video anymore, so let's give it a shot like this. Okay, so the 6 goes all the way across. It's a distance of 6 because we're out here at x equal to 6. The distance I want is the smaller blue line underneath. And this looks very similar to the last picture I had when I did it for 3, doesn't it? I've got 3 all the way over, and I'm supposed to be getting just this piece of it, right? So this piece, as we discussed before over here, is square root of x, right? It's actually the distance out that I've gone. I'm sorry, it's, did I write that right? Did I write that right? I don't think I did. This distance is x. Let me get that right. There we go. And that distance x is actually y squared from when we solved our function. So the distance that I want right here is actually 6, the whole length, minus the y squared at the beginning. So my first outer radius is actually 6 minus y squared, all squared. It's my outer radius. What's my inner radius?
3 minus y squared.
Is it? I think it's just 3. It should just be this piece right here. It's the radius of the hole. Yeah. So on this one, it's really nice and clean because I actually have 2 vertical lines that I'm going between, right? And the distance between them is just 3. So the inner radius is actually the radius of the hole, and this hole is actually a constant radius the whole time. So this one's actually minus 3 squared. And I'm integrating that with respect to y, right? We already did that, or said that, so delta y. All right, any questions on the setup so far? How about we clean it up then? Let's see, I have pi, the integral from 0 to square root of 3. I need to distribute this out, so 36 minus 12y squared plus y to the 4th minus 9. Is all good? Okay. And then we'll clean up one more time by combining the 36 and the 9. So 0 to square root of 3. I don't know how I wrote it, but I have 36 minus 9, which is what? 27. And then minus my 12y squared plus my y to the 4th. It doesn't look like a 4. Try that again. What's next? Integrate. So we need to integrate this. So the 27 is 27y. What does the 12y squared become? Close. 4. It'll be 4y cubed. And then plus y to the 5th over 5. Oops. Evaluated at square root of 3 and 0. So now I have 27 square root of 3 minus 4 square root of 3 cubed minus the square root of 5 to the 5th over 5. Man, he keeps coming up a lot, doesn't he? And then minus the 0 for plugging in 0. Oh, it is. Thank you. Okay, let's simplify what we can. I've got the pi. I have 27 square root of 3. What does the 4 square root of 3 cubed become? Good. 12 square root of 3. And we already know what the square root of 5, I'm sorry, I wrote it 5 even, didn't I? Square root of 3 to the 5th over 5 was 9. That's a 9. It really is. 9 square root of 3 over 5. Okay, we can get common denominators, we can simplify everything, and we're all real good with me just giving you that value at this point, yeah? Yeah, because this is 7th grade addition and subtraction. And if you do this, you end up getting, where am I? 84 square root of 3 over 5 times pi. All good? Okay, we've got one more axis we're going to rotate around. And I think you'll like it. What's different about this axis? It is negative, that's part of it, and then somebody else said it's in terms, yeah, it's y, so this will be in terms of x. And so this is 0 to 3. And we'll shade my shape in. But now we're rotating around y equals -1, which is actually what kind of line? It's a horizontal line, so it's down here somewhere. Oops. Okay, and this is at -1. Y equal -1. All right, so first question, representative rectangle, horizontal or vertical? Yay, we get a vertical one. It is vertical. So there's my representative rectangle. Second question, washer or disc? It's a washer. How come? There's space. There's a hollow space, right? And it's actually a constant hollow space too, isn't it? Chelsea, you're still looking at me. You don't see a hollow space.
I don't see how it is.
Okay, so I'm going to attempt one more time this whole idea of drawing. I didn't do so bad last time. Maybe we'll see how I do this time. The screen keeps getting smaller. Okay. This is going to rotate, and in 3 dimensions, it's going to look like this bowl that has this big old gaping hole right here. That space right in there is not filled in. And the way you can see it 2-dimensionally is that it's this space right here. There's space between the axis I'm rotating around and between where my actual piece that's got volume that's shaded in starts. This is the whole space. Okay? All right. Maybe I'm getting better at this 3-dimensional stuff. I don't know. All right. So I'm rotating it around this horizontal line. So am I doing this with respect to x or y? This is x. This is delta x. And I had my function that was in terms of, let me write it this way, in terms of x is y equals the square root of x. That's where I started, right? All right, so good. I'm going to integrate this now between what 2 numbers? 0 and 3. Why in the world do I get to use 3 instead of square root of 3? Because we did it in terms of x now. That makes the difference, right? All right, so now I get to go from 0 to 3. I do have a washer, which means I need an outer radius. So what is this outer radius going to be? Any thoughts? It's what?
The blue.
Part of that is the blue. Okay, so Jordan, you're seeing these awfully well. So can you tell me why in the world it's 1 plus the square root of x?
Square root of x is the distance from the line to the x-axis. And you have to
The
add
yellow part, right?
Yeah.
Yeah.
You have to add the 1 because that's the distance from the
Right.
rotation.
So it's always the distance to the line of rotation, not the distance or the object itself. So I've got to get the distance from that red line at the bottom all the way up to the top of the blue region. So yeah, I have the yellow part, which is square root of x, but I've also got this value of 1 down here that's contributing to this. Okay? This is kind of like when you go to like amusement parks in the fair. The further you are away from the middle, the dizzier you get. Have you ever had those experiences? So when you're at the middle and you spin, right, there's one issue. But when you go further away from it, your radius of what you're spinning is further out. And you have a different experience, a different feel of what's going on. That's what's going on here too, is we've got this different distance here. So we're taking a look at this as 1 plus the square root of x. And all of that is supposed to be squared, because that's my outer radius. What's my inner radius? It's just 1, isn't it? It's that constant small spot right there between that horizontal red line and, in this case, the x-axis. So this is minus 1 squared. And now I'm doing it in terms of x. Okay, so I've got something squared, which means I need to simplify that before I actually take any integrals. I have 1 plus 2 square root of x plus x, and then minus the 1 squared is minus 1. Any questions on that piece? Okay. And then what happens?
One's canceled.
Yeah, the 1's cancel, those add to 0. So I've really got an integral from 0 to 3 of 2 square root of x plus x. All right, so what is another way I could write that? Maybe that might be more helpful. I know some of you like to see this, so I'm going to write it. 2x to the 1/2, and then plus my x. Okay, if you don't have to see that to do it, that's fine, but I know some of you like to see that, so we'll do it. All right, what's the antiderivative of 2x to the 1/2? All right, 4/3 x to the 3/2, so it would have been 2x to the 3/2 divided by 3/2, which is times 2/3, so we get the 4/3. And then what? X squared over 2, and we're going to evaluate at 3 and 0, and the evaluation again at 0 is 0, so that's friendly. All right, so we have pi times 4 over 3. What does x to the 3/2 mean? Some of you have some, there. This is the square root of, in this case, 3, or x was what it was originally, and then cubed. Put the cubed under, put the cubed outside, it doesn't really matter. And then I've got 3 squared, which is 9 over 2. All of that minus 0 at the end. All right, square root of 3 cubed is what? It is 3. And then I'm going to multiply, well, 3 square roots of 3, right? And then I multiply that 3 by 4/3, which becomes, yeah, I should just be getting 4 square root of 3. Okay? And then plus 9/2. Am I able to combine the 9/2 and the 4 square roots of 3? No, I'm not. So this is actually going to not have a closed one-term form, but it's going to look like 9/2, or well, I'll just write it the way it was before. 4 square root of 3 times pi plus 9 pi over 2. Any questions on that one? Okay.